Today, we are going to talk about reinforcement learning. In particular, we are going to try to answer a very fundamental question in reinforcement learning: when can we do sample efficient exploration? The motivation is the following. If you've been following artificial intelligence, certainly you've heard about reinforcement learning, and the technique has been making headlines with impressive achievements in a variety of domains, in particular, for example, in games and in robotics. But there are still fundamental limitations to what we can do with reinforcement learning. And two core issues are sample complexity, that is normally not available in some domains. And another issue is that often those successes, they really come at the expense of a lot of fine-tuning, and these require a lot of engineering effort from the user. The core aim of the dissertation is to try to lessen some of these requirements. In particular, we work towards producing algorithms with good sample efficiency and algorithms that can scale with larger state and action spaces. So algorithms that eventually we hope they are going to be useful in practical application. In particular, we focus on providing formal guarantees for the algorithms that we propose. The setting in RL is that of exploration. Exploration is really kind of the defining problem in reinforcement learning, because an agent is interacting online with an environment. It is submitting actions and it receives states and rewards. And in particular, the exploration problem is the problem of finding a good policy starting from essentially no knowledge about the environment. And this is distinct from offline reinforcement learning. We will briefly speak about offline reinforcement learning. In offline RL, we assume that the interaction has already occurred and the agent is trying to give back some, for example, some good policy. The way we measure the performance of the agent is through regret, which is the sum of the mistakes that the agent makes compared to the optimal policy. Hopefully, as the agent is learning, the mistakes that he makes become smaller and smaller. And so the sum of the mistakes is still growing, but in a sublinear fashion. Now, when we started this investigation, the landscape of RL it roughly looked like this. We had a pretty good understanding in the scientific community about tabular methods, so methods that make an explicit representation of the state and action pairs, the transition and the rewards everywhere. And with those, we can solve fairly small problems. And for the exploration setting, we did have minimax regret readily available. But the situation was quite different for the function approximation case. Even for linear methods, people have been able to provide some guarantees for example, on policy learning, but not really guarantees in the exploration setting. And of course, we would like to move towards more general function classes, which have the potential to solve very complex tasks, but the guarantees there were basically non-existent when we started this investigation. Now, given this enormous challenge, we're going to focus on sort of the first two settings. We're going to start from tabular methods and move quickly to function approximation, in particular with linear methods. A quick overview would be this. We start with tabular settings, where we make essentially no assumptions about the model. And then we quickly move to the linear function approximation setting with a relatively strong assumption on the dynamics. And then progressively, we start to remove those assumptions with function approximation until we get to assumptions that are the typical assumptions that people make in statistical learning, which are some form of approximate realizability. And unfortunately, we will see that as we move down this curve, the situation becomes very, very challenging. We will start losing computational tractability, and unfortunately, we will also use statistical efficiency at one point. To make this roadmap more concrete, we investigate the following subtopics. First, in tabular reinforcement learning, minimax rates are available. We start to look at problem-dependent bounds, namely, can we achieve best-in-class performance when the problem is easier than anticipated, but without giving up minimax regret guarantees? This is the first question. Second one is about randomized exploration. And this second part and all the following one, they operate in a function approximation setting. And in such setting, as much as in tabular, people really focus on upper confidence bound type of algorithms. Here we take a look at randomized algorithms because they tend to work better empirically. And so we wonder whether their performance is theoretically grounded. As a third step, still in the function approximation setting, we will try to remove some of the assumptions that people make in online reinforcement learning, which happens to be much stronger than the assumptions we know are necessary in offline reinforcement learning. And as a final step, we investigate some of the fundamental limitation between offline reinforcement learning and online reinforcement learning. In particular, what's the statistical limitation of offline reinforcement learning, and what does it tell us for offline reinforcement learning compared to online reinforcement learning? Okay, I'm gonna plow ahead with the first question that we raise, instance-dependent bound. The motivation is we know minimax rates, those were, available. People have been providing sublinear regret bounds, which is kind of the minimum to ensure learnability for a long time. And then when we started this investigation, the first minimax regret bounds have just appeared. In particular, minimax means that there exists an algorithm which is as efficient as possible in terms of horizon dependence, state and action dependence, and the number of episodes. Now, this is good because for any problem you give me, you can apply the algorithm and you know an upper bound on the performance regardless of the actual structure of the problem. The question that we pose is the following, though: can we do better on specific problem classes without further information? And the contribution of this investigation are summarized in this slide. This slide is probably my favorite. I'm going to draw on the x-axis the problem class that we have under consideration, and on the y-axis the regret bound, both in terms of upper bound and lower bound for specific problem classes. Let me start by saying that lower bounds have been available for quite a long time, and most of the effort has been in providing these minimax guarantees, right, for any possible problem in your problem class, subject to the same state, horizon, and action cardinality. Now, after numerous breakthroughs, scientists were able to achieve the minimax lower bound, meaning that they were able to provide an algorithm that is as efficient as possible on the hardest possible problem. Now, we certainly care about having guarantees that apply for all problem classes, so that we don't have to worry about selecting the algorithm. But sometimes we find problems that are significantly easier. For example, bandits. Bandit problems, they have been studied much earlier than MDP, and we do know the correct scaling, and we do know algorithms that can operate in the bandit setting to precisely give the minimax regret rate for that specific setting. Mind you that algorithms for bandits, they look very different from algorithms for MDP because they don't do any deep planning. Another class of MDPs are deterministic MDPs. And in all these classes, you can imagine relaxing this assumption a little bit. For example, near deterministic MDP often arise in robotics, right? And if I ask you to produce an algorithm for deterministic MDP, well, this is very easy to do. You just try every state and action once, and you know everything about the MDP. So the algorithm you would design for deterministic MDP looks very different from a minimax algorithm, and it looks very different from a bandit algorithm. Another setting that generated a lot of interest is the setting of long horizon. So if you overscale the problem and assume that the total reward is bounded by a specific constant, empirically, we do see that the longer the horizon, subject to this bound, subject to the bound on the sum of reward. Well, the longer the horizon, the more challenging the problem becomes. We know this very well in planning, and people have conjectured that also in terms of sample efficiency, because it is something that we experience empirically. Formally, this was put forth as a conjecture in a conference of learning theory by Nanjang and Alec Agrawal in 2018, and they conjectured that there is an inevitable dependence on the horizon for problems with long horizon, meaning that we really need to solve, we really need to suffer dependence on the horizon for problems with long horizon. And then, of course, there are other subcases, but mostly I want to focus on the first 3, 4. Now, all these, we know exactly the lower bound. One of them was conjectured. And in particular, for most of these problem classes, we do know a specific algorithm that is able to achieve the minimax rate, but the algorithm is like task specific. The algorithm is designed for deterministic MDP, it's designed for bandits, or it's designed for hard instances. It's not obvious that we can automatically adapt to the complexity of the problem. And what we show in this work is, in fact, you can, meaning that you can create a single algorithm which is minimax optimal. So it is doing as best as possible on the hardest possible MDP. But then if the MDP has a specific form, a specific structure, for example, if it is a bandit, then it inherits the best performance for that setting. Likewise, in deterministic MDP, it is near optimal. And in other classes of MDPs, it matches the lower bound. And in particular, let me highlight that as a corollary of this theory, it ends up disproving the conjecture in conference of learning theory about the dependence on the horizon. In particular, we find that even if the horizon grows, you're not going to suffer if you design your algorithm well enough. Let me summarize the contribution more formally. We provide an algorithm, Euler, which is a variant of value iteration with some form of empirical Bernstein plus some other tweaks. The main result is that we are minimax optimal and instance optimal on several problems of interest. And as a corollary, we provide the first solution to this cold open problem, and we discover the long horizon RL is not harder than short horizon RL. And this work suscitated a number of follow-ups, in particular for gap-dependent analysis, and it was also used as a black box for reward-free exploration, which opened another area last year in reinforcement learning. The intuition is that most of the exploration in prior work was using often inequality, but you would really like to use Bernstein inequality, and people have been doing that in the generative model setting. The reason being, well, for one, it's tighter, but also, you see, it can start depending on problem-dependent quantity. It depends on the variability among successor state of the optimal value function. In general, you don't know all these things, right? You don't know the transition, you don't know the value function. So what we try to do here is to estimate, like to plug in the empirical estimates, plus some other correction term to ensure the validity of this empirical Bernstein inequality. This is different from the empirical Bernstein inequality that you find in the literature, because in particular, we don't know the value function. And so we have to do a specific reinforcement learning correction. And in particular, we can say, hey, even if we use the empirical estimates, in reality, it is as if the algorithm knew the correct transition and the correct value function, and was using that to construct the confidence interval, plus some correction term that decays very quickly. And so it doesn't really impact the regret, at least in main order. This quantity, the variance of the value function among successor state, is what we define to be the Q value. So this problem-dependent constant that takes a higher or lower value depending on the problem class. Okay, so this is pretty much everything for tabular RL. We're going to make a big jump now. We're going to focus on randomized exploration. And we're going to go to the function approximation setting, in which we make a linear assumption about the action value function. So we're working in the model-free setting. This is what people would like to do. You can certainly think model-based, but in general, it's more convenient to go completely model-free. And we assume that you do know the feature extractor, and you're looking for some parameter. Now, the set of all value function that are subject to this representation with varying theta is what we call the linear space for the action value function. Now, you would like to make this representation condition only for the optimal policy. So you would like to say, hey, let's assume that only the optimal action value function admits such a linear representation. Turns out that we didn't know this at the time, but later work a few months ago discovered that fortunately, even if you just assume that the optimal value function is linear, this is not enough. The problem class is too large. You have to suffer a mandatory exponential sample complexity. And so an algorithmic, or well, an assumption that people have come up with to bypass this issue, I mean, it's clear that you need stronger conditions. So an assumption that people have been making is that of low-rank dynamics. The assumption is due to Jean et al. 2020. And the assumption basically states that the transition probability matrix is low rank, surprise, and the left factor is known to you, and in particular, it lives in the prescribed functional space. So in particular, the action value function, if you look at the range of the value function, all possible value functions, right? That range is the same range as the transition probability matrix. Now, why do people make this assumption? Well, I would say it was mostly algorithmic. I'm going to give some motivation for it. Suppose that you're trying to explore with your algorithm. You start with some estimate, which is in the prescribed functional space. You have some estimate of the action value function. It might be incorrect, but it's an estimate. To explore, you would like to add some exploration bonuses and obtain some other action value function. Now, what happens when you apply the Bellman operator? Why do I bring up the Bellman operator? Well, because you're trying to compute backup, right? When you try to compute the optimal solution, or you try to run your favorite planner, you try to put optimism in the action value function, and then to perform an approximate Bellman backup. You will not know the Bellman operator, but this is a simplified setting. So let's assume you can even apply the perfect Bellman operator. You have no statistical uncertainty. While if you don't make any assumption, your value function after the backup is going to be somewhere here. But unfortunately, you need to represent this value function in the linear space. And if you try to do that, you're going to suffer some projection error. Let me tell you, this is an algorithmic explanation of where things go wrong. But in fact, the limitation is information theoretic. The assumption of low rank instead really ensures that whatever value function you come up with, after application of the Bellman operator, is going to live in the prescribed linear functional space, and so there is no projection error. Now, under this assumption, what is the state of the art? Well, state of the art was able to provide regret bounds with no dependence on the state and action space, which is extremely significant because it means we can scale to very large problems, right? And this appeared a few months before this work. And our question then is, well, this algorithm is really based on optimism, but we don't know that often randomization works much better, at least, for example, for linear bandits, and sometimes also for MDPs, right? And there are references that are able to support this claim. The question we ask here, the function approximation setting is way more interesting. Can we say anything at all about the function approximation setting with randomized exploration? And the contribution is the following. The answer is positive. We analyze the randomized least square value iteration algorithm. This is not a new algorithm. It was proposed initially by Osband et al. In 2016. The algorithm is extremely elegant. It is just the popular least square value iteration plus some noise injection, some random perturbation of the parameters. What we do is we take this algorithm, we tweak it a little bit, and we are able to show some regret bounds. Indeed, the first one for any randomized algorithm with function approximation. In particular, regret bound doesn't depend on state and action space. It only depends on the feature dimensionality and the horizon. And this is competitive with optimistic algorithm. Now, the main technical innovation is how we control the error propagation. And I'm going to go into more detail in this slide. Well, traditionally, for upper confidence bound algorithms, you're doing your sort of value iteration backward, or least square value iteration, or whatever planning method you have, and you're trying to, you have some approximate value function, and you add exploration bonuses, and you maintain optimism pretty much everywhere. And those algorithms are fairly easy to analyze. Why? Because you know exactly what you're doing. Like if you're injecting perturbation through exploration bonuses, you know in what direction you're pushing the value function. You know you're adding something to it, so you make it more positive, and so the algorithm is going to be more optimistic, right? So at least the intuition is pretty clear for exploration algorithms based on adding exploration bonuses. Now, for randomized algorithms, the situation is way more subtle because we're just adding random perturbations. So it's not clear what's going on during the planning phase. In particular, you may imagine that sometimes the noise is making you go in the right direction. Some other time is doing something potentially harmful. And so those algorithms are much more sophisticated to analyze. And the main technical innovation is we're able to analyze the randomized planning that happens in randomized least square value iteration, and we reduce it to a random walk. Now, the random walk is not a simple random walk because there are absorbing states, there are barriers, and there are all sorts of tricks to make sure that the walker ends up in the region that we want at the end of the walk. At any rate, this is kind of the overall technical contribution and the challenge to analyze those sort of algorithms. Next up is going to be exploration with Bellman closure. And here we really work toward removing some of the assumption. Why is that? Well, we know we cannot operate in the most general setting. What we just saw is exploration with low rank dynamics. That was a state of the art at the time. I think our paper was either the second one or the third one at the time operating into this assumption, which is pretty much the first for reinforcement learning with function approximation. But of course, you would like to relax those assumptions. And a natural candidate is Bellman closure. Why is that? It is that because this is an assumption that people have been making for a long time when they were to study algorithms operating in the batch setting or with a generative model. So in general, if you're doing RL with function approximation, Bellman closure is something that you heard, and it is something that is commonly used. In particular, it is a mainstream assumption that people use in offline reinforcement learning for classical algorithms like least square value iteration. The question here is, can we explore under this assumption that has traditionally been used in batch reinforcement learning? The answer is yes, but as we will see, it is going to bring some additional challenges. Let me give more detail about Bellman closure, formal definition, and how it differs from low rank. So low rank assumption, what we saw before, it is basically, it is a condition on the dynamics, but you could see it as doing the following process. You give me any value function, and through application of the Bellman operator, that is applying the transition probability matrix to the value function you give me and adding rewards. Well, if you apply the Bellman operator, it guarantees that you are going to be in the prescribed functional space. And so you're not going to suffer any reprojection error. Now, inherent Bellman error or Bellman closure is way more subtle because it still prescribes that you end up linear, but you need to start from the linear space. So if you're able to fully operate within the linear space and apply the Bellman operator, which is going to be approximate in your algorithm, well, the dynamics are such that you can still represent the value function, but you fully need to stay in the prescribed space at any time. If you start going out of the space, we have no guarantees, and in general, the algorithm may fail. Now, how do we go about designing an algorithm that is able to leverage this assumption of Bellman closure that is more general than low rank? Well, it goes like this. Suppose that we start from a linear space. What we cannot do is add exploration bonuses. Why? Because exploration bonuses they are normally a local perturbation to the value function. And so the optimistic value function that you obtain is in general not going to be linear. It is going outside of the prescribed functional space, just because it's the way we know to add exploration bonuses, right? It is adding some local nonlinearity. Unfortunately, even if you have Bellman closure, you're outside of the space. We don't know anything about what is going on. In particular, the Bellman operator applied to the value function may live arbitrarily far from the space of value function that you can represent. And in particular, if you want to maintain a linear representation afterwards, there is some projection error that we cannot quantify. So the trick for this work is the following. We try to do something different from exploration bonuses, and we try to perturb the value function within its prescribed functional space. If we do this, then the Bellman closure assumption doesn't show us that if you apply the Bellman operator correctly, you are still going to be in the linear space. Now, the actual implementation is a bit more challenging because, of course, we don't know the Bellman operator when we apply our algorithms, right? And so in particular, there's going to be some approximate Bellman operator that we are applying, but it turns out that this is not causing many trouble. Mind you that the difficult part here is to ensure optimism because, sure, we have to stay within this linear functional space, but now it's no longer clear how we will move the value function so that we can be optimistic everywhere. And in fact, you can't be optimistic everywhere. The algorithm we propose, the Eleanor algorithm, is a variant of least square value iteration with some optimization algorithm that is able to guarantee optimism at the initial state. In particular, it gives up the traditional idea of being optimistic everywhere in all intermediate state, which is what people have been doing traditionally in RL. And instead, it enforces optimism in the initial state. It turns out that such an algorithmic approach is enough. And we are able to obtain a minimax regret bound for this setting. In particular, minimax regret bound with respect to the statistical part. So we have an optimal dependence on the horizon, the number of episodes, and the feature dimensionality. And we also have an optimal dependence with respect to the violation of the assumption, meaning that what happens if the Bellman closure is slightly violated? Well, there is ways to measure this quantity, and those have been available in the literature for probably more than a decade. The quantity is the inherent Bellman error. It's really this deviation if you start from the linear space. How much is the projection error? This I quantity, while we have an optimal dependence on this quantity as well. So this algorithm is optimal both with respect to statistical error and with respect to lack of closure, so violation of the assumptions. As a corollary, if you apply this algorithm with one time step horizon, this gives the first minimax regret bound for misspecified contextual linear bandit. In particular, this linear Bellman error, this inherent Bellman error becomes the misspecification for the linear bandit case. And there are some other work that basically got to a similar result at the same time. A limitation is computational tractability. So we are not able to obtain computational tractability. And unfortunately, this is an issue of all this line of research with general function approximation. We have had quite some follow-ups. Those are also computationally intractable, and some other also focused on removing knowledge of the value of the inherent Bellman error, but still computational tractability is an open problem in this setting. This is just because we have to operate under very different assumptions, and it becomes much more complicated to do any form of planning. Now, final work. This is probably my favorite work. And you're going to see quite a shift here because we abandon the exploration setting and instead we focus on batch reinforcement learning and we investigate the limitation of batch reinforcement learning. And in particular, this is going to tell us something about the consequences with respect to online reinforcement learning. The motivation is the following. There is an increasing interest in the area of offline RL, where data have already been collected. The reason being, we have big data in the modern world, but also really exploration can be quite expensive, and all these algorithms for exploration, they come with all these assumptions, and sometimes you don't really want to trust them, and instead you might prefer some safe controller that generates the data. And also there is a lot of engineering effort to fully engineer an online reinforcement learning solution. Finally, batch RL is also a key component for online RL, because often you have some batch data and you're trying to improve the policy as a step for fully online procedure. So it does make a lot of sense to focus on batch RL and see what's going on, what are the fundamental limitations. Two are the main tasks of policy evaluation, where you've given some data set and target policy, and you require the batch algorithm to use the data set and provide a value estimate for the target policy. Another basic task is policy learning. In that case, you've given a data set and you are asked to provide the best possible policy that you can with the available data set. Those are the two basic tasks. Of course, you can add other things like safety constraint, or you may ask instead of the best policy, just some improvement with respect to the current policy that generated the data. Now, what is the setting and what are the issues of batch RL? Well, a common issue that really comes from statistics is the most basic one, the approximation error. How good is my function class? If the function class is not good, there is very little hope that we can do anything useful. How much data do I have? Do I have enough to make the prediction? Do I have any bias, any correlation in the data? Those are really coming from statistics. And quality, do I have a good data set that is covering what I'm really interested about? Let me make this concrete. Suppose that my data set comes from a behavioral policy, so a data collection policy. Well, you can imagine I am going to be able to make good predictions around this behavioral policy, but if the behavioral policy doesn't cover in some form the optimal policy, then I can say very little about the optimal policy. And likewise for the target policy, if you're doing off-policy evaluation. Now, all these are issues, and I want to get rid of them. Why? Because I am looking for some fundamental limitation of RL. So I am going to place myself in the best possible case. I'm going to assume there is no approximation error. I have infinite quantity of data, no bias, and the best possible coverage. How does this work? Well, let's look at the protocol. Ordinarily, in batch RL, you have an MDP, and this is going to give you a data set, right? Data set of state action, rewards, and transitions. And then the batch algorithm is required to make a prediction. I'm going to tick all the boxes here. I'm going to give you a function class that has no approximation error, right? So we have perfect realizability. I'm going to give you an infinite quantity of data, meaning that for the state and action that you have, you observe the exact reward and the exact transition function. So, it's really the best you can do. This implies there is no bias because I give you the exact reward and transition function. And how do we solve coverage? How do we ensure that we get a good data set that is roughly covering the area of interest? Well, we introduce an auxiliary process, and this is really a contribution of this work. We introduce an auxiliary oracle. The purpose of the oracle is to help the batch algorithm, and the oracle does know, like the MDP class, it knows that it doesn't know the exact MDP that will generate the data set, but it knows that it is contained in some bigger set. And what the oracle does is will prescribe a distribution that is as good as possible for all these MDPs. This distribution is what generates the state and action that the batch algorithm later observes. Now, we're putting super strong assumption. Let me highlight that the stronger the assumption you put, the stronger the lower bound becomes. So it's the other way than upper bounds, right? Because the more assumption you put, the stronger the lower bound becomes, because as soon as you start removing the assumption, you're even more in trouble, right? If you can find a lower bound despite working in an idealized scenario, then you might run into trouble even more so in the real world when you start having other issues that are listed here on the left. I already probably spoiled the answer. We are going to look for some sort of lower bound. And so let me give you some intuition for what's really going on. And to gain some intuition about all the assumptions that we're putting and all the framework, this Oracle framework that we created, let's take a look at the bandit model, where we know that we can easily learn the optimal solution or predict the value of a target policy. Well, let's see what happens in this case. Suppose that you have simple features like the Euclidean ball in 2D. The Oracle is trying to help the Bayes algorithm. So the Oracle is going to say, hey, let's observe values, in particular the reward function that is linear, along feature phi1 and phi2, which are orthogonal. This is the best thing, right? Because the Bayes algorithm is going to take all this data, create a linear system. The linear system is full rank. It has the best possible condition number, and it is going to solve for the optimal parameter. The intuition here suggests that there are really no problems in the bandit setting, and this intuition is correct. What goes so wrong in MDPs? Well, the MDP model is different, right? Because you have state and action. For this state and action, you do observe rewards, but you do not observe the value function. You do observe a successor state. And if you want to really estimate the action value function at SA, you need to write down some equation that relies on the right-hand side on the value function that depends on the same parameter as the one that you're trying to estimate. Now you're going to say, okay, I'm going to move this thing to the left-hand side and write down a system of linear equation. You can certainly do that. But now the situation looks quite different from the bandit setting, because you can choose, or the Oracle could choose the best possible feature. It could choose orthogonal feature, hoping that you would acquire maximum information in all directions. But unfortunately, the environment is such that the dynamics can act adversarially with respect to you. In particular, they can try to undo the learning that you've done in certain direction. So you think you're learning through orthogonal features. This is what the Oracle prescribes. Unfortunately, you don't know the exact MDP, and the MDP turns out to give you dynamics such that if you write down a system of linear equation like this, all these vectors, they are going to be parallel. And so in particular, you do not observe any numerical value for an actual combined feature in the X direction. You have no information about the X direction. Unfortunately, this is going to kill you when you have to return a prediction, or when you have to find the optimal policy. You simply have no information about what's going on in the X-axis. Now, this is the intuition. The actual argument is information theoretic. And what we discover is this. We discover that even if we put very strong assumption on the representation, so even if the optimal action value function for every policy has a linear representation, with all the assumptions that we listed before, we observe the exact reward function, the exact transition function. We have the Oracle that gives us the best distribution. We have no approximation error. We have infinite data. Even in this very strong condition, you really need basically an exponential number of state and action where you observe the outcome. Let me highlight that this lower bound that we derive is for the linear Q pi. So even if Q pi is linear probability policy, this means that somewhere in here, there is an extremely hard problem. And let me re-highlight, since we're talking about lower bounds, every function class that contains this function class, so even if, for example, only the optimal policy as a linear representation for the optimal value function, and progressively, if you consider a neural network, right? As long as you contain this class, you can find extremely hard instances. The surprising thing is that the same problem that we have here, you can solve them very easily online with an exploration algorithm designed for that specific problem. And if you also give me the assumption of a generality model, you can solve every problem in this class. So essentially, this work is really highlighting a separation, a fundamental separation that you can find between offline reinforcement learning and online reinforcement learning. I'm going to jump to the conclusion very quickly. What we've seen today, we've seen the Euler algorithm, which is the first minimax optimal and also instance optimal algorithm. I want to highlight this is an agnostic algorithm. It is able to inherit the best performance for each problem subclass, but it doesn't know the actual problem it is interacting with. As a corollary, we discovered that long horizon reinforcement learning is not harder than short horizon reinforcement learning, and we end up disproving a coil conjecture that appeared a year before this work. Second work that we've seen is in function approximation class. We have given the first regret bounds for a randomized exploration with function approximation. And by doing so, we give some partial answer to a conjecture by Jan Osband at AL in 2016, whether the algorithm was sound, like theoretically sound or not theoretically sound. The answer is yes, it is. We have also tried to remove those assumptions that characterize prior work, including ours, the assumption about low rank dynamics, which seems to be, quite strong. And in particular, we're able to give the first algorithm that is able to work under the same assumption that people used to make in offline RL. This implies that, in particular, online RL is probably not harder than offline RL, meaning that you don't need a stronger assumption. As a corollary, this is the first algorithm for misspecified contextual linear bandits. And in fact, in the last work, we see basically an even stronger claim than this one. We see that online reinforcement learning can in fact be exponentially easier than offline reinforcement learning. So there are problems in reinforcement learning that you really cannot solve offline. But if you do allow some amount of adaptivity, and you don't need much, if you allow some amount of adaptivity, then you can easily solve the problem. So those are the first reinforcement learning exponential lower bounds for offline RL. And as a corollary, offline RL can be exponentially harder than online RL. There have been a number of additional contributions. I cannot mention all of them, in particular, some about identification of bandit problems is now essentially follows as a corollary from the first part of the dissertation that you've seen. We later extended it for gap-dependent analysis. We've tried to work in the general case where we put no assumption beyond realizability of the predictor. But unfortunately, there are lower bounds, so you can sure mitigate some of the problems, but you cannot really go around the information theoretic lower bound. Then we turn our attention to very strong assumptions, and we saw that it is indeed possible to provide even randomized algorithms to work really, really well in the function approximation setting. We have relaxed those assumptions. This is the third part of the talk that you've seen. And finally, this is quite interesting, but unfortunately, in the interest of time, we couldn't go into much detail. We were able to apply randomization to provide a computationally tractable algorithm for the setting of Bellman closure. Despite, there are some other caveats, but this is quite significant because it tells that, maybe randomization is really the right strategy to conduct exploration. And then we focused a bit on policy gradient algorithms. This is quite important because policy gradient algorithms are what people really use in practice, but somehow they are not very well studied theoretically. People think they converge to local minima and all that. In reality, this is not true. Those algorithms, they perform really, really well. And in particular, they are, it's a different algorithmic protocol. And so they have other requirements in terms of assumption on the function class. And in particular, they degrade much more nicely if the assumption on the function class is not satisfied. They degrade with a much nicer notion of misspecification. And finally, we've seen exponential lower bounds for batch RL as a conclusion. Future direction, really quickly. Maybe, we have these disappointing lower bounds, which suggest there is not, an happy ending to this dissertation, but maybe we're really heading too high. What do I mean by that? I mean that in general, of course, you would like to find the optimal policy, but maybe the optimal policy is not required. Like if you're playing Go, you don't need the perfect strategy. You just need a very good policy that is able to beat a human player. Likewise, if you're doing self-driving, for example, you don't need a perfect driver. Instead, it's enough that the reinforcement learning solution be able to drive better than humans. And so can we aim maybe for some less ambitious goal? So can we make very little assumption about the function class, and in that setting, what is the best that we can really do? Another direction is still optimism is prevalent. It looks like in the function approximation setting, the story is changing because there are some of the things that you cannot really do with optimistic algorithms. Soon you're gonna hit the barrier of computational tractability. And so do randomized algorithm offer some unique advantage in the function approximation setting? This is an interesting question. And finally, policy grading methods. They are very widely used in practice. A recent theory has been suggesting that they do not converge to local minima if you use a good function class. Instead, they achieve global optimality despite the non-convexity of the problem. Can we develop some sort of general theory for those policy grading methods, similar to what people have been doing for value-based methods? For example, the Bellman rank notion. Is there any equivalent to this notion in the setting of policy grading methods? And with this, I conclude, and I thank you all for your attention.